Hi there. So today we're going to talk about section 4.5, which is titled the number E. The number E. And again, this is 4.5. Okay, so it turns out that E is a really, really nice irrational number, okay? And it comes up a lot in the quote-unquote real world. And remember what it means to be an irrational number. Probably the irrational number you're most familiar with is pi. A number is irrational if either A, it cannot be expressed as a fraction, or B, you can alternatively look at an irrational number that when it's written in decimal form, it's non-terminating and non-repeating. In other words, it goes on and on and on forever with no rhyme or reason. Okay? So, we're going to be talking about the number E quite a bit. I will tell you that E is approximately 2.71828, etc. It goes on and on and on. So the way you want to think of the number E is it's a number between 2 and 3, closer to 3. Okay? Now, we use the number E because things in calculus, it turns out, work out the nicest when we're dealing with logs of base E. So, when we're dealing with our logarithms, in our next chapter, okay, one of the very nice bases that we'll be dealing with is base E. Again, the reason why is because in calculus things work out much, much nicer. Okay? And the thing that I'm going to tell you is I understand right now we haven't talked about logarithms. We will actually in the next section. But when we talk about our base of E in our exponentials, which pertains to this chapter, you know to use the base of E when it's a continuous growth. Now, a formula that we saw in the last section was this. Remember, we looked at this in terms of like looking at a bank account. The principal was the amount that we put in the account. This is our rate. This is the number of times per year interest is compounded, and T was the number of years. Okay? Now, so remember, our N changed depending on how many times a year interest was compounded. So if interest is compounded, say monthly, we had N to be 12. If it was weekly, N is 52. If it was daily, we use N to be 365. But what if we want to talk about interest that's compounded, what we say continuously? Okay? When we talk about that, we're saying, hey, let's let N get super duper large. In other words, let's let N go to infinity. Well, it turns out that if we just look at 1 plus 1 over N to the nth power, okay, so I'm just letting R be 1 just for the sake of it, and then our N's be N, T is 1. If we let N go to infinity, it turns out that this quantity actually goes to the number E. Okay? You don't need to know the whys or the wherefores. This is actually something that's proved in calculus. Okay? But what this gives us is a way to compound interest, what we say continuously. So the 1 plus 1 over N, it turns out is E. Okay, so one of the things we're going to see is that when interest is compounded continuously, here is our formula. Okay, so we have the P This part is our E, there's our R, and there's our T. We will use that soon enough, but I wanted to at least show you where this number E comes from, okay? So the key thing to remember is this is used for continuous growth, okay? So let me give you the definition here. A definition we have is for the exponential function, and we wrote it as Q is A times B to the T power. The continuous growth rate, that's a key word, K, is given by solving e to the k equals b. Then what we get is Q is A e to the kt. Okay? Now, one thing to note, when A is greater than 0, so I'm just going to say when A is greater than 0, one of the things that we'll see is that if our exponential is written in this form, if K is greater than 0, we have growth. And if K is less than 0, we have decay. All right, so a few of the things that we're going to be playing with is converting back and forth between the exponential function form that we've looked at in addition to our exponential form like this. Now, we will need to introduce our logarithms, but let me do an example here. All right, so for example, what if I have y equals 7 e to the 0.02t? Okay, this is my initial population, just like we had it. Okay, I claim when this is given in this form, we're given our growth rate. Our growth rate here, just change this to a decimal or change it to a percent, is 2%. Okay, now what's another example where we can talk about our various growth rates? Well, another example where we have our growth rates are as follows. What if I have, say, y equals e to the, how about negative 0.23t? Okay? Now, I can ask you a few different questions here. One question I can ask you, for example, is what's our initial quantity? Remember, that's still the number in front, so that's going to still be the number 1. And then the next question I can ask you is this quantity going to be increasing or decreasing with time? Okay, notice my k is negative here, therefore we know it's going to be decreasing. Now, what is the rate at which it decreases? It decreases by 23%, and we would say continuously. Alrighty, so let me do a couple more examples here. Let me write down 2 examples. So suppose I have 2.7, 0.12 to the t. Actually, I'll probably do more than 2 examples. And then I'm going to do Q is, who cares, 3, 1.04 to the T. Q is 5, e to the 0.3 T. And then here Q is 7, e to the negative 0.15 T. Okay, now for each of these, I want to know what is the quantity at time 0. I want to know, is the quantity increasing or decreasing over time? What is the rate at which it is? And is it increasing or decreasing continuously? Okay, these are the 4 questions that we would like to answer. Okay, so for this first guy, okay, what is our initial quantity? I claim here it's 2.7. What's our initial quantity here? It's 3. Our initial quantity here is 5. And our initial quantity here is 7. Notice it's always the number in front, because if you plug in t equals 0 in any of these guys, well, just like 0.12 to the 0 power is 1, e to the 0 power is also 1. Okay? So now let's ask ourselves, are these increasing or are they decreasing? Well, remember, the way you can tell when you have a base of B is if B is greater than 1, it's increasing. And if B is between 0 and 1, it's decreasing. Because my base here is between 0 and 1, I know that this guy's decreasing. Because my base here is greater than 1, I know this one is increasing. Now, when you have this written in exponential form, and again, we'll see how to go back and forth in the next chapter once we learn about logs. The way you tell whether it's increasing or decreasing is literally, is your exponent positive or negative? So since this is a positive exponent, this guy is increasing. And since this is a negative exponent, he is decreasing. Okay? Now, what is the rate with which each of these are increasing and decreasing? Well, remember, when it's between 0 and 1, 1 minus the rate gives you the base. Oops, 0.12. Okay? So, well, 1 minus 0.12, I claim that this is decreasing by 88%, right? Because 88 and 12 give you the 100. This is increasing, remember it's 1 plus the rate, by 4%. This guy is increasing, well, literally you just read it off, it's increasing by 30%. And this guy is decreasing by 15%. And the only ones that are increasing or decreasing continually are the ones with the base of E. Continuously, so yes and yes. All right. So that is one example of what we're looking at here, just again to get you familiar with this base of E. All righty. Now, what if I ask you to look at these graphs and say, without a calculator, what we want to do is match the following graphs. One of these guys is e to the x. One of these guys is 2 to the x. And another one is 3 to the x. All right. Now, how would we identify which graph is which? The key thing to remember is E is about 2.7. So it lies between 2 and 3. So how do we know which graph is which? Well, I think you'll grant me that the larger the base, the faster it grows. So I claim this first guy is growing the fastest. Therefore, who has the largest base? I claim he's got to be 3 to the x. He's growing in the middle, so he's e to the x. And this guy's growing the slowest, therefore he's 2 to the x. Okay? Again, what's really important to me is that you get the general gist of what's going on here. Okay? All right, so some more examples that I would like to do are as follows. Okay? Let me ask you the following. Okay, suppose you're given this. Suppose you are given the initial quantity. So the initial quantity, let's say, is 100. And let us say that we have a growth rate of 5% per unit of time. Okay? So, what I want us to do is write the formula for this exponential function. First, if this is not viewed as a continuous growth rate, and then if it is viewed as a continuous growth rate. Okay? Remember, if it's not a continuous growth rate, it looks like this. And if it is a continuous growth rate, you've got your base of E. Well, what would our formula look like? Either way, our initial quantity is 100. That's the number out front. If it's not a continuous growth rate, remember that's when you use either the 1 plus the growth rate or 1 minus the decay rate. Here we're growing by 5%, so we would write 1.05 to the power of t. If it's a continuous growth rate of 5%, we would write e to the 0.05 t. Okay, these are not equivalent. Clearly, this is going to grow faster when it grows continuously. Okay, so another example. Okay, suppose I write down a few populations. And what I want us to do is just discuss each of these in words. Okay? And I'm just going to go through and verbally talk about these. This first guy has an initial population of 200, and I claim it is growing at a rate of 2.8%, okay, per whatever unit of time. This one has an initial population of 1,000, but I claim it's decaying at a rate of 11% per unit of time. This next guy has an initial population of 50, and I claim that he's growing by 20% continuously over that period of time. And this last one is has an initial population of 700, and he is decaying, because it's negative, at a continuous rate of 17%. Notice whenever I have a base of E, I'm talking about it continuously growing or continuously decaying. All right, next. The next one that I'm going to look at is I'm going to tell us that a town has a population of 3,000 people initially. And what we want to do is we want to write a formula for the population of a town, P, in year T, if it, let's say, grows by 200 people per year. Now what I'm doing is I'm really trying to take everything that we've done and put them together. Okay? So if it grows by 200 people per year, notice this is a linear function. It's growing by a constant amount. It's not a percentage. So we would say, well, we start out with a 3,000 plus 200t. Okay? What if now I'm going to say that it grows by 6% per year? Now this is an example of an exponential. Again, the 3,000 goes out front, but now I have 1.06 to the power of t. Okay? What if I say now it grows at a continuous rate of 6%? Again, we have P is 3,000. Since it's continuous, we have E to the 0.06t. And let's do 3 more, just to be sure we've covered all of our bases here. What if now we say that the population shrinks by 50 people per year? This is a linear. So again, I start out with 3,000, but since it's decreasing, my slope is negative. What if now I say that it shrinks by 4% per year? Well, we still have our 3,000, but now remember we take 1 minus the percentage, so we have 0.96 to the power of t. And last but not least, what if now we want to find a formula, but now it shrinks at a continuous rate of 4% per year. Well, we still have 1,000. We see continuous, it's E, and we put negative 0.04 to the T. So hopefully all these examples have helped you kind of figure out how to write these formulas and at least distinguish whether your formula has an E or not. Now, as I mentioned at the beginning, one of the things that we're going to be doing is compounding interest. And the moment you see in a problem that interest is compounded continuously, then you want to use this formula. Let me show you an example, okay? Suppose we deposit $5,000 for 10 years, and we want to know how much is in the account if, part A, let's say interest is compounded with an APR of 2%, or let me just say at a rate of 2%, and let's have it be compounded quarterly. Okay, this is what we did in our last section. We just need to fill in the appropriate numbers. We deposit $5,000. My interest rate is 2%. We're compounding quarterly, which means 4 times a year. N is 4 and T is 10. Now, if we really care what that answer is, we can certainly do this computation. And we will see after 10 years, we have $6,103.97. Now, let's contrast that, but now we want to know how much is in the account if interest is compounded continuously at a rate of 2%. Whenever you see that something is compounded continuously, you want to use this PERT formula. Okay? Plug things in very much the same way. We're investing $5,000. We have E, our rate is 0.02, and our T is 10. So we compute E to the 0.02 times 10, multiply that by 5,000, and we have $6,107.01. Notice, it's not a heck of a lot more. $4 over a period of 10 years is nothing to write home about. On the other hand, it does make sense that if something is compounded continuously, it's going to have more than, say, if it was not. All right. Next. What if we want to compute the following? Okay? And this will be our last example because this will really sum them all up. I want to know which is the best and worst investment after 2 years? Okay? So, we have investment A. Investment A, we're depositing $875 at 13.5%. Oh my gosh, this like does not happen. Compounded daily for 2 years. We're going to have investment B be $1,000 at 6.7% compounded continuously for 2 years. And last but not least, we're going to have investment C, where $1,050 is deposited at 4.5% compounded monthly for 2 years. Now, really, the only way to know which investment would be the best is to actually do all the computations. I mean, let's talk about the differences here prior, okay? Notice, here we're depositing the least amount, but we have a high interest rate, and it's compounded more frequently, for example, than this. So if we compare, for example, these two, here we're depositing a fair amount more, but at a lower interest rate, and it's not compounded as frequently. Notice this guy has an interest rate in between the two, but he's compounded more frequently. And he also has a deposit more frequent. He also has a bigger deposit than this one, but not as big as this guy. So let's actually see what we get. This will be fun. Well, A is our principal, 1 plus the rate, which is just crazy, 0.135, over, what is our N? Since it's compounded daily, it's 365, and this is raised to the 365 times second power. All right, and in case you really care, what we're going to get for this first guy is we're going to have $1,146.16. Okay? So, how much money did we make by this? Well, do you guys agree? We made $271.16 off of investment A. How did I get that? Well, I took my ending amount minus my beginning amount. Okay? Now let's compute this guy. Again, it's P, our principal, E to the rate 0.067 times 2. Okay? And if we compute this, our ending balance is $1,143.39. So if we subtract off our beginning amount, we made $143.39. So between the two of these, clearly this is our better option. So now what we need to do is compare it with this guy. Here we are starting out depositing $1,050. We don't have a very big interest rate. And let's see what we get here. 1 plus 0.045 divided by 12. Now why is it 12? Because I'm compounding it monthly. And we will see in the end here we get $1,148.69. And if we subtract the 1,050, that's actually the worst of them. So, in this case, investment A is clearly our best option. All right. Now, one last thing that we need to talk about is the effective rate. Okay? You remember in our last section how we had the nominal rate, but then we had the effective rate. Okay? Now, the way you compute your effective rate when you're dealing with continuous compounding is literally you compute E to the whatever the continuous growth rate is. Continuous growth rate. So, for example, if I told you that the nominal rate for some investment is 6%, remember, that's what we would get if we compounded it once a year. But the effective rate is actually higher. Again, why? Because we get interest upon our interest. So if you're going to compute the effective rate, if your nominal rate is 6%, you would compute e to the 0.06. What you're going to get is this. Okay? So our effective rate is actually 6.184. Okay? Remember with our other formula, you do 1 plus r over n to the nth power. Okay? But here, all you need to do is compute e to the power of r. All right. That completes section 4.5. Thank you.